Thanks for coming. So now Andres is here,
And they invite to speak.
and he asked me not to start the
Mixture.
seminar without him. All right. So we're pleased to have Daniel McGinnis, who's visiting here second time, right before his PhD. Now he's at Princeton to talk about surprising sufficient and necessary conditions. Okay, please.
Thanks. Yeah, thanks a lot for giving me the opportunity to speak here. So yeah, this was something that I worked or thought about a lot during my PhD, and then last fall. Oh yeah, so I met Nikola. He's a PhD student at Freie University in Berlin, and I told him about this problem. And just last fall, he emailed me again and was like, "Oh, have you been thinking about this problem? Maybe we should work on it." And then together we were kind of able to finish the details. So it's really nice. So happy to be talking about it. Okay, so kind of like the classic theorem in discrete geometry that kind of gave birth to a lot of these interesting problems is Helly's theorem. So Helly's theorem states that if you have, so the setting is we have F, which is a finite family of convex sets in Rd, and it has this local property that every d+1 sets in F have a common point. So every d+1 intersections are non-empty. And the conclusion is that, well then, the whole family F can be pierced by a point. What I mean by pierced by a point is just all the sets in F intersect. So if every d+1 sets intersect, then all the sets intersect. So yeah, pierce, you can just think of it, there's one point that kind of is hitting all the sets in F. Yeah, so just a little demonstration. So if we're in R2, and I have this family of 3 convex sets, and right now, yeah, if I want to add another convex sets to the family that maintains this condition that every 3 sets have a common point. So if I add, say, this red set, to maintain this condition, the set has to have a point in each of the pairwise intersections. And then so Helly's theorem is saying then this new set would have to intersect the triple-wise intersection of the previous 3. So, for example. Okay, like I said, Helly's theorem, a lot of interesting questions came out of Helly's theorem. For example, like what happens when you say weaken this local condition. What happens when you take more general or maybe more restrictive families of sets rather than just the convex sets? How does the conclusion change, etc. For this talk, I'm going to be talking about a variation of this theorem, where instead of trying to find a point that hits every set in the family, we'd like to find a higher dimensional affine subspace that hits every set in the family. So we'd want to find conditions that guarantee that a family of convex sets can be hit by a line, for instance, or a plane, etc. Okay, so in this direction, we have the following definition. A k-transversal to a family of sets F and Rd is just a k-dimensional affine subspace that intersects each set in F. So for example, in Helly's theorem, it's about 0 transversals. So a point is a 0 dimension. Yeah, a point hitting every set in the family is a 0 transversal. Okay, so the obvious extension, or the obvious generalization that you could think of Helly's theorem, say for k-transversals, doesn't really work. So, for example, Vincenzini asked this: does there exist a constant r, depending on k and d, such that the following holds? Any family of convex sets F and Rd with the property that every R sets of F have a k-transversal must itself have a k-transversal. So for Helly's theorem, this R exists. So for Helly's theorem, this is k equals 0, and this R is d+1. And so this statement would sort of be like the natural generalization of Helly's theorem that you would first think of. But it turns out that this isn't true. So Santalo provided counterexamples. So he showed that this is false for all k greater than 0. So the obvious generalization of Helly's theorem that you would think of doesn't work. In fact, there's a kind of a funny story. Vincenzini didn't just ask this question; he actually proved this. And then Santalo was like, "No, there are counterexamples." And then if I remember right, I think Vincenzini even tried to publish another proof after this. And yeah, didn't work. All right, but yeah. So the question is, what kind of condition do you need to guarantee that you have like a 1 transversal or 2 transversal, etc.? Because this, like I said, the first thing that you would think of doesn't work. So the first positive progress in this direction was made by Hadwiger in 1957. So here's the statement that he came up with. So again, we have a finite family of convex sets in R2. Okay, so he does the two-dimensional version, I should say. But he has this, for his proof, he needs this additional condition that the convex sets are pairwise disjoint. And he says that such a family has a 1 transversal if and only if, so this is going to sound weird, but I'll explain in a second. We can linearly order the sets in F such that every 3 sets has a 1 transversal consistent with the ordering. So what I mean by there's a linear ordering on F, I just mean like you have a set C1, C2, C3. We're just ordering them like that. And every 3 sets has a 1 transversal consistent with the ordering. That just means, for example, if you have set C1, C2, C3, there should be a line that hits them, but it should hit them in the correct order. So it should hit C1 and then C2 and then C3. So it should hit them in the right order. So here's just a little example. So the dotted line here is just demonstrating that there's a 1 transversal. And okay, so here the numbers is the linear ordering. This is set 1, this is set 2, this is set 3, this is set 4. And let's check that Hadwiger's condition holds. So I need a line that hits 1, then 2, then 3. So there's 1. I need a line also that hits 1, then 2, then 4, and this line also does that. I need a line that hits 2, then 3, then 4. So there is 1. And I need a line that hits 1, then 3, then 4. And then yeah, the conclusion of Hadwiger's theorem is that you do have a 1 transversal. So yeah, so...
Well, maybe not in that order.
Yeah, so the 1 transversal doesn't have to be in the order that you gave the set. So for example, this transversal hits 1, then 2, then 4, then 3. So that's why this example is kind of interesting. Just a little side note, if you strengthen this condition, every 4 sets has a 1 transversal consistent with the ordering, then then you can guarantee that you have a 1 transversal in that order, that hits them in that order. Let's see. All right. So yeah, that's Hadwiger's theorem. Okay, but the question here, of course, is at this point, is this pairwise disjointness condition really needed? He needed this for his proof, but it's not clear if you really need that. And also, what would the higher dimensional versions be? So he did this for 1 transversals in R2, but what about your sets are in RD? And if you want to pierce with a general K transversal. So this, generalizing this to higher dimensions was open for a long time, and it wasn't until about a little over 30 years later until some progress was made there. Okay, so it was generalized for hyperplane transversals in RD, so D-1 transversals in RD. And this is sort of going to be the the condition that guarantees a hyperplane transversal, or D minus 1 transversal. Okay, so we say a finite family F of convex sets in RD separates consistently with the set of points P in some lower dimensional space, so yeah, so some points P and RK, and I'm thinking of K as being less than D. If there exists a map phi from the convex sets to the points, so basically I'm associating my sets with points in a lower dimensional space, such that we have the following conditions on subfamilies of size at most d plus 1. So if the convex holes of the points associated to these subfamilies intersect, that should mean that the convex holes of the sets that they came from should intersect as well. So basically you can sort of think of this as like you're modeling your sets as points in a lower dimensional space such that you preserve this sort of intersection property. And notice that, if I take little side note, if I take a subfamily of size d plus 1, then a convex hole like this will exist by it's called Radon's theorem, kind of another classical result in discrete geometry. So this is sort of has some relationship with Radon's theorem. And I'll say in a second why this condition recovers Hadwiger's condition in the two-dimensional case. So yeah, the theorem, it was really proven over a series of 3 papers.
Can I ask you a question?
Yeah.
So does this function phi need to be a bijection or?
No.
No.
Yeah, two sets could map to the same point. Yeah.
I see.
Mm-hmm.
So whenever they are mapped into the same point, then they should always intersect or something like that?
Yeah. Yeah. So the theorem for hyperplane transversals was proven over a series of 3 papers. Goodman and Pollack first did it, except they needed sort of a disjointness type condition on their family of sets. Wenger figured out how to remove the disjointness condition for Hadwiger's theorem, and then Pollack and Wenger figured out how to do it in general for hyperplane transversals. So yeah, they proved a finite family F of convex sets, no disjointness condition, has a d minus 1 transversal if and only if it separates consistently with a set of points in Rd minus 1. So they really found the correct condition to guarantee a hyperplane transversal. But at this point, finding a condition for a k transversal where k is between 0 and d minus 1 is still open. Okay, so yeah, back to the Hadwiger's theorem. So the map here is, after you have your linear ordering, so linear ordering is basically the same thing as I'm going to map my set 1 to a point that's all the way on the left, like compared to the other points. And then set 2 comes next, set 3 comes third, set 4 comes fourth. So it's like, it's the first way that you would think to map these things to R. And so if you satisfy the separating, so to check that it satisfies a separating consistently condition, I have that, for example, the convex hole of phi1 and phi3 intersects phi2. So that means that the convex hole of set 1 and set 3 should intersect set 2, which it does. And that's the same thing as saying that there's a line that hits 1, then 2, then 3. Yeah, so that's the basic sort of translation between separating consistently. Yep.
So it's not if and only if condition, it's just if they intersect, then the corresponding thing should, the convex hole should intersect, right?
You mean
if and only if and only if.
Yeah.
No. I mean the implication is only to the right.
Yeah. Yeah. Mm-hmm.
And another thing is it clear that for any family of convex sets in some dimension, like k bigger than d, you would have this?
For any
meaning just does any finite family of convex sets separate consistently with some set of points somewhere?
You can do it in its own dimension.
Yeah.
Yeah, in its own, but
So you could put k equals d.
so is it immediate? Wow.
Just choose a point inside each convex set.
And just choose
Aha.
points inside each convex set.
I see.
Yeah, and then
This implication is
Cannot span something larger than dimension one.
I need to know something.
Okay. So yeah, this was basically how it specialized the Hadwiger theorem. And actually, I want to show a proof of this. And the tool that I'm going to use for this proof is called the Borsuk-Ulam theorem. So it says that a continuous map from the n-dimensional sphere to Rn, which has the additional property that's antipodal. So that means that f of x equals minus f of minus x. Yeah, so if you take a point on the sphere, the value of the function when you look at its antipode should be the negative. And then it says that such a map has a 0. So it maps to 0 in Rn. Okay, so it's I want to say the proof because it's kind of neat, and also similar ideas are going to be used later. Okay, so first I'll do sort of the sketch when d equals 2. So this is Hadwiger's theorem with no disjointness condition. So the first step is you put your copy of R2 sort of lying in R3. You can think of this as being the z equals 1 hyperplane in R3. You want a copy of R2 and R3 that doesn't go through the origin specifically. Okay, so what I do is I want to use the Borsuk-Ulam theorem, so I'm going to take my sphere in R3, and and I'm going to sort of describe how to define the map. So first I take a point on the sphere. This will correspond to a directed line in R3. So I have this arrow here. And then what we do is we take our sets that are lying in this copy of R2 up here and we project them down onto this line. And what I'll do is define these points for each of these projected line segments, which is just, so each of these points, I'll define, they'll just be real numbers. So it's just going to be the distance to the origin, the distance, the distance to the origin, and it'll come with a sign, positive or negative, depending on where the line is going. So this would get a positive number here, and this would get a negative number here, and this one would get 0. And then the whole point is, how am I going to find my line transversal to my sets? The point is that, I forgot to mention, the way that we define these numbers is antipodal, because if I switch the direction of the line, then this number, which was positive, now becomes negative. So, and same here. And how do I find my line transversal up here? What I do is I just take the orthogonal complement of this line. That will be a plane in my R3, and then it'll intersect up here in a line. And the point is that I want to find a line such that all of my sets project onto the origin. Because if they all project onto the origin, that means my orthogonal complement will intersect all of my sets. And then that will be my line transversal. Mm-hmm. So the goal is to use the Borsuk-Ulam theorem to find a point such that every one of my sets projects onto the origin. Okay, so how do we define the map? So, So I take my my p's. And so, yeah, the map sort of has two parts. On this left here, I take my p's and I take the sum. So this will be like a real number. And this is going to be a weighted sum of these phi of f's, which, if you remember, they're points lying in Rd minus 1 in general. So this is an Rd minus 1. So in general, we'll have a map from the D sphere, and then this will be an Rd. And what does it mean? And this will be antipodal, it'll be continuous, etc. And what does it mean to have a 0? Well, either all of my P points were 0, which means that everything projected onto the origin and I'm done, or it means that these sums are 0, but some of these P's may not be 0, and that's an affine dependence. So basically the only important thing is that if you have an affine dependence, it means that you have a pair of set points whose convex holes intersect. It basically means that if you take the phis with a positive coefficient in front of it, and you take the phis with a negative coefficient in front of it, those 2 points their convex holes will intersect. So just a little technical thing, just the point is that it means 2 convex holes intersect. So
sorry, but what was the P? PFX?
that was these points. So you project, and then you take the distance of the origin.
Okay, but what was the phi?
The phi was coming from the separating consistently definition.
So that it was a given thing.
Yeah, it's given. Yeah. Thanks. Okay. And if it separates consistently, that means that the corresponding convex holes for the original sets intersect. So again, we just take these F minuses where this P was negative. You take the subfamily F plus where the P was positive. And the separating consistently definition says that since these convex holes intersected, that means these convex holes will have to intersect, but we get a contradiction. They can't intersect. And yeah, let me just show a picture. The F plus lie on this side of the hyperplane. Or sorry, I guess arrow's pointing this way. So the F pluses lie on this side of the hyperplane. The F minuses lie on this side of the hyperplane. So their convex holes will be disjoint. So that's the contradiction. Yeah.
But in the definition of separated consistently, you have this condition on the size of the families.
Oh yes, good point. I forgot to mention that. So yes, so we have an affine dependence among these phis. It follows from Kirchberger's theorem, which is another kind of classical result in discrete geometry, that there's an affine dependence among d plus one of them. Yeah, and then so you can restrict to just a size of d plus one sets. Yeah, thanks for bringing that up.
Sorry, so is this basically the original proof of Wenger and Pollack?
It's modified. It's a little different.
But they still use the Borsig.
Yeah. Yeah.
But it's more or less the same, no?
More, so here you take a map from the d-dimensional sphere to Rd. They take a map from the d-1 dimensional sphere to Rd-1. And actually, I think their proof is less malleable. Yeah, because they take this hyperplane and they translate it along its normal. But if you have a smaller, say if you have a line in R3, it's hard to translate it. Like you can't just translate it along the line. Yeah. So that's why it was crucial to come up with this proof, even though it's similar. Okay. So the basic strategy to come up with a K-transversal theorem was to find a proof first and then figure out what condition would pop out, basically. But first, to describe what condition we ended up finding. I just want to write this separating consistently definition in a slightly different way using affine dependencies, because that's like the only way that we'll be able to describe the result for the k-transversals. So this separating consistently condition is equivalent to the following. So it's a condition that, so again we have a finite family F and we have a phi, and it's equivalent to for every subfamily F prime of F. So we're thinking of F prime as being like the union of F1 and F2. So again we can take it to be size at most d plus 1. And for every non-trivial affine dependence here, we can think of like the original F1 here as being the sets that had a positive coefficient, and F2 as being the sets that had a negative coefficient. So if we have a non-trivial affine dependence among the points, the phi points, then we should be able to find points QF in our sets and real numbers, non-negative real numbers, I'll explain in a second, such that you get basically the same affine dependence among the QFs in your original sets. So again, this is the reason why we need this to be non-negative is so that the signs of these coefficients don't change. So it really means that the correct convex holes of the original sets are intersecting. Yeah. So yeah, this written in terms of affine dependencies means if you have an affine dependence among the phi points, then you should have the same basically affine dependence among your sets. And yeah. Again, just little technical stuff, but it's just a rephrasing of this. Okay, so now I'll describe the condition that pops up for k-transversals. And it's going to be a little ugly, so just bear with me. So again, the setting is we have a finite family of convex sets in RD. We have a phi that maps from F to a set of points in RK, and here I'm doing k-transversals, so I'm really thinking of, so for hyperplane transversals you could think of this k being d minus 1. Now I'm thinking of it as being k corresponding to k-transversal. Okay, so here's a condition. We say that F is dependency consistent with d minus k tuples in P if for each subset, and now we only have to check subsets whose size is at most k plus 1 times d minus k plus 1. I'll say more about that in a second. And for any d minus k collections of affine dependencies among the phi points, so before we just had one affine dependence, now I have a collection of d minus k potentially different affine dependencies among the phis. Then I should be able to choose points in my sets in non-negative real numbers such that essentially the same d minus k affine dependencies hold between those QFs. So it's like the same definition that I showed in the previous slide, except now we have more, you have to satisfy more affine dependencies at the same time. So a couple of important notes. When k is d minus 1, then this number becomes d plus 1. So you get the same number as in the Goodman-Pollack-Wenger theorem. And again, when k is d minus 1, you just have one affine dependence. So you really do recover the exact same definition I showed on the previous slide. So this condition recovers the hyperplane transversal condition. Another thing is when k is 0, so this is in the realm of Helly's theorem, you again get d plus 1 here. So you get the same number as in Helly's theorem. And while it's not easy to eyeball it, but this condition ends up being equivalent to Helly's theorem, to Helly's condition. So this condition is perfectly interpolating between Helly's theorem and the Goodman-Pollack-Wenger theorem hyperplane transversal theorem. Okay. So yeah, I just want to give a rough idea of how the proof goes here. It's similar to the one that I just
You
showed.
didn't say the theorem though.
Oh yeah, yeah. I'll say the theorem and then I'll say the proof. Yeah.
That's the right order.
Yeah. Here's the theorem. Yeah. So I fix a k between 0 and d, and f is a finite family of convex sets in Rd. Then there exists a k transversal to f if and only if f is dependency consistent with d minus k tuples in a finite set of points p in Rk. So yeah, like I said, a little bit weird condition, but it's a thing that works, and it does perfectly give you Helly's theorem when k is 0, and the Goodman-Pollack-Wenger theorem when k is d minus 1. Okay. So, yeah, so that's the main result that we proved. So solving basically the question of what are necessary and sufficient conditions that would guarantee one to have a k transversal to your family of convex sets. Okay, so now I'm going to say the proof. Okay, so before we use this Borsig-Ulam theorem, now we're going to use a different, but still Borsig-Ulam type theorem. And so the thing that's going to replace the sphere is going to be a thing called the Stifel manifold. So, but the Stifel manifold WKRD, this is the space of orthonormal k-frames. So it's a little weird, but a point in the Stifel manifold corresponds to k orthonormal bases in Rd. So a point is a set of k orthonormal bases.
What is the frame?
Yeah. Sorry?
What is the frame?
Oh, it's just orthonormal bases or orthonormal.
You mean
Like
k-
unit
Oh,
vectors.
yeah, yeah,
K pairwise orthogonal.
yeah.
Unit
So
vectors.
this-
Yeah.
because it's not the basis.
It's not a basis for Rd.
But-
Oh, right. Yeah, it's not a base. So yeah,
It's a basis for K flat.
Yeah.
For K dimensional subspace.
so linearly independent unit vectors. Yeah. so a point in the Stifel manifold. You can think of it as an ordered tuple, because the ordering does matter, actually. So these WKs it's a set of linearly independent unit vectors in Rd.
So
Also,
do you
Or
also,
orthogonal.
Pairwise.
Yeah, sorry, I don't know what it is,
Orthonormal.
but pairwise orthonormal, yeah.
so in the definition, do you also consider the negatively oriented basis? As
Yes.
an element? Yes.
That's a different point.
Yeah, it's a different way.
So it's kind of a sphere for a Grossman.
Something like that.
Yeah.
yes.
Yeah, so when k is 1, you get back the sphere. Because if k is 1, you just have one orthonormal vector.
Yeah, I said that it's like a sphere for Grossman manifold.
Yeah.
Right, it's a parametrization of that, or of the Grassmannian.
And the Borsig-Ulam type theorem that we're going to use is the following. So every continuous Z2K equivariant map, I'll explain that in a second, hits the origin, basically. And what I mean by Z2K equivariant map is that so there's a natural Z2K action on the Stifel manifold, which is just I can independently make each component negative. And then you have the same action on here. You have k copies of Rd minus k, and you can independently negate the k copies. And Z2K equivariant just means you respect this action. So if I negate, it means that I have a continuous map such that if I negate some components in here, then when I apply the function, you also negate those corresponding components. So
maybe you can just say that if you substitute k equals 1, you really get the Warsaw products.
Yeah, yeah. Mm-hmm.
Is that too equivariant? It really means f of
Actually,
minus x is minus f of x.
yeah. Oh, actually, in this case, you don't actually get the Warsaw theorem because when k is sorry.
You do
Yeah, you do.
SD
My bad.
minus 1 to RD minus
Yeah. There's actually the thing that I was thinking of is there's actually a slightly stronger version of this result, but this is the only one we use. But, yeah. And I'll say this was proved explicitly in 2020 by Chen, Frick, and Hull, but really this was proven probably a little less, around 40 years before, but it appears sort of implicitly.
Sorry, why there is a d minus k in there?
Because it's on the steep for k manifold.
What do you mean why?
What should be? Yeah. So it is about the k frames in
In RD.
yeah in RD, but why there is d minus?
Well, there's a slightly stronger version where instead of rd minus k to the k, you have, I think it's rd minus 1, or rd minus k. Is that, wait, should it be plus 1?
plus 1, yeah.
Plus 1.
Maybe it's supposed to be
Okay,
like this.
components, huh?
I think it's supposed to be like this.
Yeah.
Yeah. This is a strong. This stronger version is actually true, but we only need this one. So
And who proved it implicitly?
I think it was by Fadel Husseini. They came up with this index theorem, and I think they were able to prove this.
4 years earlier, or 40 years earlier.
40.
40.
Oh,
Yeah.
40.
40.
Okay, that makes more sense.
Okay.
They came up with a simpler proof though,
Mm.
which is nice. Okay. So now I'll say the basic idea. So before we took a sphere, we took a point on the sphere, and then we took the line generated by that point essentially. Now we're going to take the Stifle manifold. We're going to take a point in the Stifle manifold, which is a k-frame, which spans a k dimensional thing. And then we're going to project. So we're going to project basically, instead of projecting onto a line, we're going to project onto a higher dimensional thing. So I'll just do a proof sketch when codimension is 2, because that way we can visualize it a little bit easier. So I'm going, basically what you do in general is we're going to define a point from, if we want to find a k transversal, we're going to define a map from the d minus k Stifle manifold and our d plus 1. So what we'll do is, again, we'll take our convex sets in RD, we're going to place them again in RD plus 1. So that's why this RD plus 1 is here. So in the codimension 2 case, we're going to have, this is going to be the relevant Stifle manifold for the codimension 2 case. So what you do is you take a point in the Stifle manifold, and then again it's going to be a k-frame, so it's going to span some k-dimensional flat. So in this case, since we're doing codimension 2, this d minus k will be 2, so I'm taking a 2-dimensional plane inside RD plus 1. And then, yeah, you do the same thing. So you project your sets onto this plane, and then you do, again, almost the same thing. For each set, you take the point that's closest to the origin. And there is always a unique such point because these sets are convex.
So they are in the same plane, right? So
Yeah, they're all in the same plane, yeah. We projected them down. And yeah, so here's how we're using the convexity. Since these sets are convex, this closest point really does exist. And now these p points, before they were numbers, now it's a vector. It's a 2-dimensional vector. In general, it'll be d minus k dimensional. Okay, and then something to note is that if I take a point, so say for this set, if I take a point in the original set corresponding to this one, and I project it down, so I took a point Q, I projected it down, because this blue set is convex, this vector, which is the closest point to the origin, and this vector corresponding to this point, their dot product will always be positive because this is convex. And that's going to be something that we use in the proof as well. So I won't go into as many details, but basically we define this map essentially a similar way as before. So here, Pi just means, so again, P was a d minus k vector. Pi just means I'm taking the ith entry, so this is a number. And then again, I have this weighted sum of the phi's. But now I have d minus k of them. So this is an r, this is an rk, so this is an rk plus 1, and I have d minus k copies. So it really is a map into here. And then we do the same thing. It's going to have a 0 by that Borsuk-Ulam type theorem. If so we have two cases. If all the PIs are 0, then we're done.
Sorry, can I?
Yeah.
So this I, can you say again what does I index?
That's the ith component of the target space, no?
So we're
Yeah.
so in our case I is equal to, I mean, it's running from 1 to 2.
Yeah, 1 to 2, yeah. So yeah. P1 is just the first entry of P. Yep. So yeah, if all the PIs are 0, that means everything projected down onto the origin and we're done by, similar arguments that I showed before. You take the orthogonal complement, this will be a K transversal in your original space. And then the other case is, well, you have d minus k affine dependencies among the phi's, and then you use the affine, or the consistent or dependency consistent definition. And again, I'm going to gloss over some details, but once you pass it through the dependency consistent definition, it means that you have an affine dependence among your sets. Well, you have d minus k affine dependencies among your sets. And when you project, so this is just a property of affine maps. When you project, you still preserve the same affine dependencies. But what it ends up implying, having these affine dependencies, again, I'm leaving out details, but these affine dependencies imply that when you sum over all sets, these kind of dot products with these Q points will be 0 when you sum over all sets. But like I said, each of these dot products are positive, so that can't happen. So that's the contradiction that you get here. And it may sound different from the contradiction that I mentioned in the proof of the Goodman-Pollack-Wenger theorem, but really you could phrase it in the same way. You'd just be projecting your points onto that line, and it comes out the same argument, essentially. Okay, so that's roughly how the proof goes. And now you might be wondering, well, it's nice that the condition, it works for one, and it interpolates between Helly's theorem and Goodman-Pollack-Wenger theorem, but could you realistically actually use it on a problem? Like, could you apply it to something? And thanks to Andreas, we do have a nice application. So after we put our paper on archive, he reached out to us and mentioned this really nice application. So actually, we can apply it to give another proof of a theorem that was already known. So let me just explain what the theorem is. So the setting is we have some finite point sets in RD, say these k plus 1 finite point sets. And the theorem is that we can find a k-dimensional affine subspace T such that every closed half space that contains T has this proportion many of the points from each AJ. So this is called the central transversal theorem because, yeah, you can kind of think of it. You have this k-dimensional affine subspace T sort of lies, I guess not in the middle of the AJs, but it kind of has to lie within the AJs for you to have this property, and that's for each AJ. So yeah. When this theorem was first proved, it was really nice because it generalized an old result called Rado's center point theorem, which is the case when k equals 0, which was proven like in the 1930s. So this was 60 years later, and they were like, oh, there's this really nice generalization of this result. The other thing is that their proof of this theorem is, I would say, significantly more complicated than the proof that we can give of it using our k-transversal theorem. So
k equals d minus 1 is also a well-known theorem, I think.
oh yes, yeah. So when k equals d minus 1, that's ham sandwich theorem.
Right.
Yeah. So kind of both extremes were well known and well established before they proved this. So yeah, one thing is it would be nice to find more applications of our theorem. I mean, this one is really nice, and it really ties in the result with the known literature, but nice to find other applications. Another little open problem, I guess, is to find a colorful analog of our result. So the colorful analog would be, I guess we would have d minus k times k plus 1 families, and you sort of are dependency consistent among like colorful tuples, roughly speaking. And then the conclusion you would want is that is there a k transversal hitting one of the colorful or one of the families? A colorful version of the Goodman-Pollack-Wenger theorem is known, and that's a result by Andreas, and there's a really nice proof there, but it's not clear like how to generalize that proof to this setting. Okay, and I think that's all I want to say, so thank you for
Questions?
So I have two questions. So if we assume the compactness on each convex set, then we know that the Helly's theorem is still work for the infinite convex families. So is it still true for your theorem? So if you assume the compactness, then we can.
Yeah, I believe if they're compact, then you can reduce the problem to just finite set. It's a finite family of sets. Although off the top of my head, I don't know the details
I think
on that.
that's right.
Yeah.
It's just compactness principle.
Yeah.
And my second question is, how do you prove the converse direction, the other direction?
How do you prove what direction?
If only
Oh, I see. Yeah, great point. I forgot to mention that. Okay, yeah. So I showed the proof to this implies this. So this implies this is just you take a k transversal to your f, and then you just take for each set you take a point on the intersection of the k transversal in that set, and it will be dependency consistent with that set of points. Yeah. Thanks for that question. Yep.
So is there any kind of fractional analog? Or would it be something interesting from that point of view? Like fractional Helly?
I think it's a good question.
Yeah, I don't know. Yeah.
I guess there's no algorithmic aspect, right? Because you use this topological method.
Yeah. Unfortunately. Yeah. But the same is true for the hyperplane case as well.
So hyperplane is not, there is no algorithm right now for doing this.
I don't think so because it uses Borsig-Ulam theorem.
So instead of a single K transversal, if you are interested, if you can cover the whole thing with P, K affine sets, do you think we can formulate some reasonable theorem or?
Sorry, what was?
So instead of having a single K affine set, I'm interested in whether we can hit everything with P.
Oh, I see.
Yeah.
I see. So you, okay. So there are results like if you have a family of convex sets in RD, and say for every P sets, some D+1 have a hyperplane through them, then there exists some constant number of hyperplanes whose union hits all of them. That's the analog of that theorem for K transversals doesn't hold. Whether you can sort of weaken this condition to get some number of K affine sets whose union intersects F, I'm not sure. That would be interesting. I haven't
When you
thought
say
of it.
the analog doesn't hold with this kind of definitions,
I meant like
because previously people didn't have anything like that, right? This
But the PQ for hyperplanes doesn't have that condition. It's really just there's some hyperplane.
Oh, yeah.
intersects
Ah,
them.
okay,
Yeah.
okay.
And that doesn't work.
Okay,
Yeah,
that's
in the-
yeah, that I know.
Yeah.
So the same question restricted to R2. How about that? Is something known?
Yeah, there everything is known.
Everything is known.
Because I think a line in R2 is a hyperplane. No?
Yeah. So it's known in R2 if every 3 sets have a line, and there are 3 lines whose union hits all the sets. So this is a theorem of me and my advisor Shira. I talked about last year actually. Here.
Also uses topology.
Yeah, also uses topology.
So, is there? I'm not sure that this question is really makes sense. But can there be any weighted method generalization?
That's a great question. I'm not sure. Because the weird thing is that in this condition, it's like for oriented matroids, how you pass through like affine dependencies and the oriented matroids, just you only care about the signs on your coefficient.
Yeah.
But here it's like we don't only care about the signs. It was like because these numbers RFs have to work for all D minus K affine dependencies. So it's not just the signs that matter. For the hyperplane transversal case, only the signs mattered. But now, since these numbers have to work for all D minus K affine dependencies, the values, not just the signs, but the values of these numbers also come into play. So, maybe there's something, but I'm not sure exactly what it would be.
That's the one with the lines.
Any more questions? So if not, let's thank the speaker.